So if I were to go into the homework and assessment and look for a test that I wanted to retake, say if you didn't have a chance to complete module 5 or 10 tests yesterday, you could go back to it and request an extension. So let's look at how you would get there. I just used the general homework and assessments link from our course homepage just now. And get into student view. I know yours looks slightly different, but you should have my assignment shown at the top. Click there. And then on past assignment, there's a button at the bottom of your list that should say past assignment, or maybe at the top even. If not, it should be down here. And then I've got module 10 here I could go to, or I'm also going to scroll up and find test module 5. Could also do any of these homeworks. So I'm just going to click on here, test module 5. And that red highlighting is new to me. Don't be discouraged by that. See this button right here that says go to request extension and then click over to automatic. That's where it may not be immediately clear because it doesn't look like you have any option immediately, but if you click over to automatic and then down on accept, then it's registered. You have to close this window and refresh or come back to the assignment and see now I can enter my answers. So go through those steps. If you ever need to request an extension on anything, it should allow you to automatically using the automatic button. Okay. Are there any questions that you had for me from module 5 or 10 from last week? Any questions for me from module 5 or 10? Ready to get started on what we have for I know some of them you are going to find challenging, and so make your best effort on those. Raise them as questions to me when we're together if you want to. Maybe take a mental note somehow, put it in your phone or write it down if you ever want me to go over one. So are we ready for today's stuff? Ready to go? All right. So module 6, this is actually the first 2, maybe even into the 3rd week of college algebra. This is exactly what you would start with in the college algebra class in the fall, is this stuff that we're going over today. Solving equations, and in particular in section 6.1, doing things like adding or subtracting the same quantity from both sides of the equation, or multiplying or dividing the same quantity from both sides of the equation. And we'll also throw in some fraction practice as well. I want you to take a look at that first example where it says solving of the form x plus something equal another number. And let's do the one that says x plus 4 equal 2. If we eyeball that, what number do we need in this place in order for this to be true? 1 plus 4 equal 2. Check yourself. Yeah. 3, 3 plus 4, 7. You can do trial and error as long as you want. 2 plus 4 equals 6. So what about that 2 do we need? What needs to be with that 2 in order for this to work? A negative, right? A negative 2 plus that 4 would give a 2 in the end. So that's just kind of like trial and error method. That doesn't always work with every single equation, but ideally you would be able to kind of narrow down what the right number is with that kind of thinking. What we want to talk about this week is how do we formalize some strategies of getting there that we're not always relying on doing things and changing the number over and over in our heads and checking them. So one thing that we can say about this equation is that we have variable quantities, I'm going to label those VAR, and we have numerical quantities. And there's somewhere in this packet where it says this exactly. I don't see it on 6.1. It may be on the 7 packet. But the goal whenever we're solving the equation is to collect those things that are variable on one side of the equation and those things that are numerical on the other side of the equation. So here we have variable plus numerical equal numerical. We need to move this numerical over there. To collect all of them on that side, have only our variables on the other side. I'm going to rewrite this x plus 4 equal 2. How can we move that number to the other side to join with that 2? We want to, if there's addition or subtraction of some numerical number, numerical piece, then we take the opposite operation. We say minus 4. And to balance the equation, take that same operation on the other side. X plus, now we have nothing more with that x, equal, and then 2 minus 4 for our negative 2. So that's formally how we get there. This kind of equation could be framed in a variety of different questions. It could say, check that x equal negative 2 is a solution of this. And we would plug it in and see if it works. Yes. Solve for x for this equation. Do this kind of thing. Find that it's negative 2. A couple of different ways that that could be framed. And the basic strategy is that if we're adding and subtracting some numerical part of the equation and need to move it to join with the other numerical parts, then we take the opposite, either subtract if it's adding up here or add if it's subtracting up here. So let's look at a slight alternative of this. If we had x minus 4 equals 2, that's a subtractive 4 there. So take opposite operation to join those numerical pieces. What would we do? Plus 4. So that we eliminate that number over here. Just have x plus 4 over here. What do we get? 6. Think of multiplication. Mhm. So we looked at similar equation framed just slightly differently right there. Notice how the operation is similar in some ways, but just very slightly different. And so the numerical answer is also slightly different. So that all falls in the realm of addition or subtraction to get to our final answer. Look at the second example where we have negative 3 over 4x equal 12. So notice the difference in how that's written. We don't have a plus or a minus sign in that equation. It's just a number or numerical part next to the variable part equal a number on the right-hand side. And so we read this as multiplication going on between that 3/4 and the x. And to undo multiplication, we can take the same quantity and divide it. So divide negative 3/4, divide negative 3/4. That's going to effectively divide evenly right there, leaving us with x right here. Now this is kind of complicated. I would read this divide symbol, write it this way, and recall when we were doing this before, we flipped the fraction that came after the divide symbol, right? So 12 times the flip is negative 4 over 3. And I'm going to come back here to my whole number and just write it over 1 so that I'm looking at two fractions next to one another. I can then say times the numerators, 12 times 4, 48. 1 times 3 for the denominators is 3. And I've got a negative, and one of them negative. Can I simplify that? Go ahead and check this in your calculator to see if it divides evenly. If not, then look for factors that they both share. What do we find if we just do a division check on those two numbers? $16. So it divides evenly. Then we can just write that 16, bring our negative with us. So not too bad there, even though that multiplication was a little complicated with the fraction. We applied the opposite operation. Instead of times this negative 3/4, we divide it so that it divides from the left, getting the variable by itself, and then divide it similarly over there. This required a little bit of recall on that fraction setup for division. I'm going to come in and do some additional examples here on the multiplication and division. We just had number times variable equal number. So let's look at another one like that. Let's say 7 times y equals 21. Notice this time it's not a fraction right here. It's whole number 7 times that variable equal another numerical part over here. So what do we want to do? divide something over here? Yes, I think that's a good idea. What exactly? Divide the 7. And so our 21 on the other side is getting divided by 7 as well. So that's the kind of fundamental setup for undoing that multiplication. The opposite is division of that number to get just y, and then we get 3 here. Okay. Yeah. What about negative 5y equal negative 21? Same structure, right? So nothing really is going to change about what we do, except the number itself can be divide negative 5 here, divide negative 5 here, y equal, and we got 2 negatives, so that makes positive 21 over 5. Not as clean an answer there, right? Because 21 and 5 don't divide evenly, and also they don't have any shared factors, so we would just leave it like that. We did simplify it a little bit in dealing with these signs. Let's do a over 3 equal 8. A divided by 3 equal 8. We can read that as. And I'm just continuing in the same sort of avenue as the second example of 6.1. Using multiplication and division to get the variable by itself. This one has division going on currently, and so the opposite would be multiplying. Yeah, there's no symbol there, so it's understood to be there. Multiplication. Yep. When you just have number and variable next to one another, assume it's multiplication. Good question. So recognize those cases as implied multiplication. Here it's more explicit, right? Divide bar. So under that division, we're going to say 3 times. 3 times. So 3 divide 3, that cancels. 4 divides evenly, leaving us with A. And then we do that 8 times 3, we get 24. One more where we combine the two. Let's say that we have 3y over 2 equal 17. We have both cases going on now. We have a 3 times y, like this, and a divide 2, like this. So you can break it down however you want. I'm just going to start by getting rid of my denominator. The times 2 on either side. And that will get rid of the divided 2 on the left. Divide, and I'm left with 3y. And just do this in my calculator and get 34. Now I'm at this stage. I can just do divide my 3 that I have. Divide 3. Divide 3. 3's divided here, leaving me with y. 34, I check that, divide 3, I get a decimal. And so I can't take anything out of both of those. 34 over 3. We've got in example number 3 there, the distance equals how fast you're going rate times how much time. It says car travels 55 miles an hour for 3 hours. How far has it traveled? It says to figure out that distance, we would say, okay, how fast does it go in R? 55 miles per hour. How long? T, 3 hours. So we multiply those and we get 165 miles. It's an application of an equation there. More evaluating like we've done in previous week than having to solve like we just talked about. Let's just kind of look over those problems and see how you would approach them. Is -3 a solution of that equation? How would you go about doing that? Checking to see if -3 were a solution. Looking at that very first problem on the section 6.1, this equation is -3 a solution. How do we do something like that? Yeah. Let's substitute or plug in -3, and then work out both sides individually to see if they get the same result. So 3, plug in here, -5 equals 4, plug in here, -9. Now get in there with that -3. So -9 from that multiplication -5, -12 from that multiplication -9. I get -14 over here, I get -21 over here. That's not equal. So no, -3 is not a solution since we didn't get agreement, right? That's how you would approach something like that. Numbers 2 and 3, you would approach like we just talked about, either adding the same quantity to both sides or multiplying or dividing a quantity by either side. And then number 4 has a slightly new idea embedded in it. Number 4 in your practice problems list says 4x minus 11x equal -14. Remember, I like terms. If we see those on one side of the equation, then we can combine them before continuing. But since both of these have x to the first power in them, let's operate on them and combine them to one term. What is it? 4x's minus 11x's -7. Oops, 7. Operate on your front numbers, 4 minus 11 for -7. And then I'm going to bring down this. And then it becomes exactly like this problem. Notice. Same structure. How did we get this -7? Oh yeah, next step, divide both sides by -7. So that's good old 1 over here, x and positive. Those negatives are going to rule out. 14 divided 7 for 2. And I'll show you some techniques when solving equations that look like proportions next. But I want to stress practice, practice, practice 6-1. Make sure that you are just so confident in 6-1 that nothing's going to throw you. Okay? These other sections are valuable in that they kind of flex your understanding of 6-1, solving equations. And so they'll help us. But by the end of this week, you should be feeling really solid in the stuff you see labeled 6-1. So I would stress doing like the homework section of 6-1, where it says 6.1 HW. Proportions are set up where we have fraction on one side, equal fraction on the other side. For example, as you see on the page there, 4 over x equal 8 over 15. And that's how I want you to translate when you see on the page, it looks like this with the slashes. You can translate to this format. And then we can apply some of what we have talked about earlier. We can say, okay, in order to get rid of these denominators, I'm going to multiply by x here and x here. Why? Because that gets rid of it right here, leaving me with just 4. Times something on a fraction goes to the numerator. Okay. And I always think of it as over 1, and so therefore that piece is going to the numerator. 1 times 15 is on the bottom. Then I'm going to do that over here. Get rid of my 15 by multiplying it on both sides. Divides evenly here, leaving me with 8x. Do this multiplication calculator if you need, 60. Now I'm looking at one of those like here or here. So I can say, okay, get rid of this times 8 by dividing it. And that leaves me with just x equal 60 over 8. Doesn't divide evenly, but I can see that there's some factors that they share. So maybe you divide 2 on each. 30 over 4. Still see factors in there. So I'm going to divide 2 again. And I get 15 over 2. There we go. Those don't have any more. So 15 over 2 is what we get. Now, remember our kind of guess and check trial and error strategy that we talked about when we first started? Plug in a number 2, 3. That would never work there, right? That's why these formal strategies are useful, because I bet you I wouldn't even guess in a million years that the number needs to be 15 halves going in there. That's why these kind of things are good to develop and practice carefully. Make good organization of your work so that you can go back as you need It's not every time will you get immediately to the right answer in the first try. So that's solving with a variable in the proportion. Let's look at this first practice problem from 6.2 that says, determine whether the proportion 7/15 equal 28/60. Kind of like, do they equal? How do we figure out? Yeah, you can do that strategy. Yep. 15 times 28, 60 times 7. That will tell you. In the interest of just showing you some of these equation solving mechanics, I'm going to do times 15 on both sides. So they divide over here, leaving me with 7 equal 28 times 15 over 60. Because remember, times something on a fraction, you throw it to the numerator. And then I need to do times 60 to get rid of it on the denominator on the right. So that leaves us with 28 times 15 and 60 times 7 over here. Isn't that what you told me? Yeah. So that's seeing it from the more formal strategies of solving equations. Okay. And does it check out? Yes. 420, it looks like, on both sides. I can also see it visually right here. If I were to scale this fraction, times 4 is how I get to 60 right there. 15 times 4. If I check that same number times 4 here, it does give me 28. I don't expect you to recognize those patterns, but I just wanted to tell you so you could potentially see something like that as well. Number 2 is just like this one, so you can practice that one. Number 3 on the practice problem is a little complicated. It says x plus 2 in parentheses slash, so I write that slash as over 5 equal 9/11. So let's just go through it with formal strategies. You can do cross multiply strategy so long as you are accurate in that approach. But I'm just going to do formal equation solving times 5 on each side so that I get rid of my 5 here, leaving me with x plus 2. And throw my 5 up here over 11. Then I'm going to do times 11 times 11, but all of this is times 11. So I'm going to bring that set of parentheses back in to make sure I'm multiplying 11 times everything. My 11s cancel over here. So that gives me 45 from 9 times 5. Cancel 11. Now let's distribute 11 times x and 11 times 2 for 11 times x plus 11 times 2, 22. Now we're to that number is added or subtraction kind of step, where we would take opposite of either addition or subtraction here. Subtract 22. Get rid of that 22 on the left, leaving us with 11x equals 45 minus 22 is 23. Now we're at the division stage. 11 times x. Get rid of that by divide 11. Divide 11. And so, and over here we have x by itself from 11 canceling here or dividing evenly. 23 over 11 on this side. And that doesn't divide evenly if we check it. And 11 doesn't have anything common with 23 otherwise. So we're done there. That last practice problem on 6.2 was a bit more complex than some of the others. That would be a nice kind of goal to work toward. However, I wouldn't hang your hat on being able to do that necessarily by end of this week. I'm more interested that you could do one like this, where we don't have that grouped amount. We just have a single x over here in this first example, right? Here we're building toward a little bit more complexity. It'd be nice if we're getting comfortable with that kind of complexity. But like I said, this is kind of like first goalpost that can come later as needed. We have some percent examples of using equations on 6.3. And kind of the go-to setup for percent equations is that if you're looking for blank percent of something is a certain amount. For example, 75% of 20 is what? 20 is easy to cut up into quarters, right? This is 3/4. So 1/4 of 20 is 5. 3/4 of 20, that's 15. Now let's check that mathematically. 75% is 0.75 times 20. What do you get in your calculator? 0.75 times 20. To get that 15. So we kind of thought through it intuitively here. We checked it mathematically in our calculators here. Now, to do it mathematically, you need to get that percentage into decimal form before you do. Look at the first example next. It says 45% of what number is 18? 45% we have percent 45 of what? So we don't know the base here. Is 18. What do I need to do with my 45 here to make this correct? Notice I didn't write down my percent sign. The 45 of the whole number is wrong, right? What do I need? Yeah, I need that decimal in there. And then how do I solve that kind of thing? Number times don't know equal number. What do I do? If the 18 were here, I would agree with you. 45% of 18 is what? That's what you're answering for me. Let's write it down in a way that is similar to what we were doing earlier. We have 0.45 times the base equal 18. How do I undo or solve that equation? Number times variable equal number. What do I do? Over here, divide, right? Divide that number which is multiplied on the variable on both sides. So we're dividing 0.45 here. And what do we get? 18 divided by 0.45. Hmm, 40. So there we got it, 40. Come back here and just do a gut check. 45% of 40 is 18. Does that make sense? Almost 50%, right? So what's almost 50% of 40? 20%? 50% of 40? Half? So 18, a little less than half. That intuition may not come to you immediately, but it is good to have sort of gut checks or benchmarks that you can check yourself on. More like 6-1. That's what I stressed earlier. Make sure by the end of this week you got 6-1 down the most. These other applications of equations, you can see are not immediately like what we were doing in 6-1, but they can be expressed as such here. And likewise, percentage problems can be set up like proportions, like we just looked at. For a lot of percent problems, it makes sense to read them off as blank percent over 100 equal the amount over the base. And you may have at some point even heard is over of equal percent over 100. So let's look at that second example, example number 2. It says an 18-karat yellow gold necklace weighs 25 grams and contains 9% copper. How many grams of copper are in the necklace? So the entire weight is 25 grams of this thing. 9% of it is copper. So let's take that out and say, okay, 9% over 100 is what amount of 25 grams? If we set it up in that way, then we can figure out that either by cross multiplication here or the formal method, I'm just going to write this times this is 9 times 25 equal 100 times our amount. And then 9 times 25 is 225 equal 100. I'm going to start abbreviating here, A. How do I solve that? got 100 times A right here. I can get rid of the 100 times by dividing 100. Divide 100, divide 100. Looks like I'm going to get 2.25 is the amount of copper in grams, 2.25 grams. I want to do this third one on the practice problem because it gives you a really awkward percent to work with. 0.5% of what number is 9? 0.5%. I can do 0.5 over 100 is 9 of what? I'm kind of calling on this way of looking at it right now. The percent number over 100 is 9 of, don't know, of what? So then I can do my solving. If I were to look at this in this way, then I don't know the base. So it would be 0.5% times my base equal 9. I like this strategy better. It makes more sense to me. But if you find you like the other one better, that makes more sense to you as you look at these, then feel free to go either of those two routes. The thing that I feel like makes this a little simpler is that oftentimes it can be read directly from the words in the question. So I've got 0.5%, place that over 100, of what means I don't know that. So in place of what, you can just put your favorite letter. I'm going to put Y there. Is goes here, 9. Then I can use like cross multiplication strategy. 0.5 times Y equal that way 100 times 9. So I got 0.5Y equal 900. Divide 0.5. What do I get? 0.5 on 900. Confirm for yourself, you get 1800 there. While you're doing that, let me just state for the record that we'll go over 6.4 and 6.5 on Thursday. We'll wrap up with some questions that you have